Okay, let's begin. We'll pick back up where we left off and overlap the where we left off last time. And where we left off, we talked about software-generated interrupts or traps. And this is a figure from the book, and it talks about the relationship between a trap or software-generated interrupt between the relationship between the kernel and some application that calls that so-called system call. Now, typically, kernels can only perform or will be the only entity on your computer that performs so-called privileged operations. And a privileged operation is anything that interacts with one of those resources. And the reason why the kernel is the only one that does it is so that it can arbitrate between multiple programs that might want to access those resources. Another reason is that so it will keep apart different programs that could potentially conflict one another or damage one another. One such operation is to move pieces of a program into and out of memory. And as you can imagine, if a program did it on its own, it could very easily overwrite the code for another program, right? That's how many viruses work, and certainly there are ways to circumvent that, those protection mechanisms. That's why when you get a security update, it's really important to update that because someone has found some way to circumvent the protection mechanisms. So the kernel is protecting programs from one another. Another example might be to read or write a file, right? If you can read or write a file and you don't own that file, you're now doing potential harm or damage to other programs that might be using that file. So imagine a banking application. You go to the server, the website for your bank, and then you want to draw funds. That's going to end up updating a piece of information in a database, ultimately stored somewhere on disk. Another program comes along and it wants to do the same thing. Now, of course, you need the kernel on the server that's going to make sure that your transaction will not alter the data for someone else's transaction in the database. So in this diagram, we have the user process in pink, or if that's red on top, and then we have the kernel process. A process is nothing more than a program in its executable state. Now, when it's not executing, it's just code stored somewhere in memory or on disk. So going from left to right, we have our user process, and this user process is executing in its normal way. And then let's say, for example, it wants to write a file, write a piece of information to a file, right, regardless of what that information is. So it calls a system call, file read, or rather file write, and that's made available to it by the operating system. There are a standard set of so-called system calls that every operating system makes available to every program that can run on that particular operating system. It's part of the development APIs, application program interfaces, or library or collection of functions made available for folks who write applications. And of course, this is different for Windows, for Mac OS, for Linux, and so forth. Now, because you can write applications in multiple languages, they have so-called multiple language bindings, meaning a set of APIs in the various languages that you can use in order to write applications. Okay, so the process calls, say, a file write operation, and that file write is called by this process. It's a user program, and it does not have the privileges or the ability to write to the disk directly itself. So this is called, and it calls into the operating system, and a trap is generated, an illegal operation. You, this user process, are trying to execute something, file write, that you're not allowed to do on your own. But fortunately, you specified the file contents to this file write system call. And when it traps, one of the things that happens in the service routine for this interrupt, the operating system looks up in a table somewhere which system call was that initiated this trap or this software interrupt. So now it looks up and it sees it's the file write. So then it calls into the operating system, and the operating system says, okay, well, I'll do this on your behalf, right? You're making a request. So traps are used not only just to protect programs from one another, used by the operating system, they're also used to transfer control from a user process temporarily to the operating system for the purpose of executing the details of one of these privileged operations. And in the example I'm using today, we're going to use a file write. So As payload or parameter to that file write, it includes a buffer of information. Transfer of control happens from the user process to the operating system kernel, and then this mode bit is set to 0. So now privileged operations can be performed. So the operating system goes along, merrily executing the system call, and now that we've had our discussion on I/O devices and buffers and things like that, the operating system kernel sets up the transfer of data between memory, right, corresponding to that parameter of the file write, and the buffer for the I/O controller attached to the disk. So it specifies the correct information indirectly through the controller, and then the system call is executed. So then the platters of the disk spin up. The read-write head seeks to the right tracks and sectors on this disk. It does the write operation, and then the operating system is done performing that write operation on behalf of the user process. So now control is now handed back to the user process once this privileged operation is done. So the mode bit is set back to 1, and control is passed back to this user process. The program counter is loaded with the next executable instruction corresponding to the code that just follows the system call in that user process. And then this user process hums along merrily, executing the details of the code that define it. Okay. Any questions about this? Okay. Make sense? Okay, so we left off there last time. Let's continue on with the new material. Process management is another responsibility of the operating system. And as I said before, a process is a program in execution, right? So that means parts of that program should be loaded on the CPU, and the CPU is now decoding those instructions and performing the actions encoded by whatever those instructions happen to be. Could be to add things, it could be to divide things, it could be a floating point operation, it could be a logical operation, it could be a comparison. It doesn't matter what it is. So in order to run, this process needs a bunch of resources from the rest of the system in our von Neumann architecture. And some of those resources include certainly time on the CPU, right, because you need to execute. It includes memory, because you might need to store things, and it might create new data that you have to store, and you have to store it someplace. You might need I/O requests, so you're going to touch some device, and more correctly, you're going to interact with the I/O controllers associated with those devices. So if you're dealing with a network program, like say your browser, you're going to interact with the network card, right, through the network I/O controller. Likewise for disk, you're going to interact with the disk I/O controller if you're going to read or write things with a disk. You're going to deal with files, right? You might be opening files, you might be reading files, you might be sorting files. And you also have some bootstrap data that you're going to use as part of your startup. And once this process is done, right, it needs to terminate. And termination doesn't just mean it stops running, it also means restoring those resources back to a known state, initial state, once you're done, because you need to free up memory, for example, so that other programs can use it. Okay, so termination of a process means that you're going to reclaim any of the resources that were used. So let's take a little bit of a look at processes. Let me see if I can change the pen here. Starting to get better at this. Okay, so we have the bus for our von Neumann architecture. And then let's say we have main memory. And I'm going to try to draw it bigger. And you also have your CPU. Let me put this down here so I can write a little bit more neatly. So here's your CPU. And I'm going to draw that a little bit bigger. So we have memory, we have CPU, and then we also have an I/O controller in our von Neumann architecture. And hanging off of that I/O controller is our disk. Okay. And I'm going to draw that pretty big. So again, for a CPU, we have a number of components that collectively comprise our CPU. We have our arithmetic logic unit, or ALU, right? Those are for arithmetic operations like addition, subtraction. We have our floating point unit, FPU, right? And those are for operations involving decimals. So if you're going to raise things to exponents, do multiplication, do division, the FPU is involved. Now, of course, we didn't talk about this a lot last time, but we talked about it a little bit when we mentioned caching. So we have our instruction cache. I'll just call it iCache. And then we also have something called a data cache, dcache, right? And so instruction cache and data cache are part of that cache that you read when you look up a chip specification for your main processor when they talk about level 1 and level 2 cache, right? The iCache and dcache, instruction cache and data cache are part of that level 1 and level 2 cache that they refer to. Now, the instruction cache is used to pull in pieces of your program and include those instructions on the processor. It's very fast memory, this instruction cache and data cache, but it's very small relative to main memory. We also have our register file. I'll call them registers, reg, and you have a small number of these, and as we discussed before, those are used as scratch working space for temporary values. So when you have local variables in a program block, you're using your register file or registers from your register file. When you say add two numbers and you say A equals B plus C, well, when you compute the B plus C part, that temporary value, namely the sum, has to go someplace, right, before it's assigned to A. Now, the place where it goes is in your register file. Likewise, you also have something called the program counter, or PC, and the program counter contains the address or the number identifying the next memory location where an instruction can be found for your program to execute, right? And then another thing I did not talk about, there's something called the stack pointer. And the stack pointer refers to the memory location for the stack, right, where the top of stack is. And a stack, you all should have taken, did everyone take data structures? Data structures, okay. A stack is used when you implement function calls, you being the compiler. It's used to store the parameters for the function as well as some of the local variables. Not all of them, but some of them. Then you also have some memory registers. I'll just say mem. And the memory registers tell the CPU what the boundaries are for the block of memory in RAM that the program occupies. Okay, so we also have our main memory. And of course, one of the things that's in main memory is your operating system. The code for your operating system, right, initially came from disk, and it's stored, or parts of it are stored in RAM. Likewise, your program, so let's say you're running Microsoft Word, right, and that's in memory, and let's say you have Internet Explorer, IE, or whatever it's called now, running. Okay, so your process is the executable form of each of these bodies of code. They start out on disk and they're loaded into memory, right? So they just didn't get there magically. They started out on disk and they were loaded. Parts of them were loaded into RAM. So we started out with our OS on disk, and when we bootstrapped loaded, the CPU initiated a transfer for parts of that to be loaded into RAM, right? Likewise for Microsoft Word, as well as for Internet Explorer. So now the operating system is running, and you double click on, say, Internet Explorer, right? You double click on it, and it knows, because it's associated with the icon you clicked on, that you're going to run Internet Explorer, right? So let's assume that was already in, parts of it were already in memory. So the first thing that happens is all of this information that's on the CPU right now, if the operating system is going to switch from whatever happens to be running, including itself, to some other piece of code, the system needs to remember what's in the ALU, what's in the FPU, what's in the register file, the current value of the program counter, the stack pointer, memory, instruction cache, and data cache. So it needs to put it someplace. Let me ask you, where can it put this information that's on the CPU? If you're going to switch, that means you're going to switch back, and you have to remember what you were doing when you last left off, right? So where might you put all this information that's currently stored on the CPU? Anyone? In the cache? Not really in the cache. That's close. Where could you put it? So we have here, right? We have memory. right? Is memory a good place to put it? Is it? No? Who said no? You did. So Sia, is that right? Sia says no. Why not? Why isn't memory a good place to put it? What do you think? In memory? In main memory? But why? You do. So what do you think is one reason? What's one reason why you won't put it in memory? Okay. So let's think about this. You have Microsoft Word, and that's a pretty big program. You have Internet Explorer, and that's a pretty big program. You have lots of other programs. If you have Dropbox, if you have email, right? So how big do you think Microsoft Word is on disk? When you install Office, it's a few gig, right? How big is RAM? How big is RAM? Pardon? 8 to 16 gigs. Okay. So let's say Microsoft Office together, you're going to run all of Office, it was 20 gig. What would happen if you loaded all that information into RAM? You'd fill it up, right? So the Y part, you can't store in memory. Memory is a good place to put it because it's fast, right? But the problem is that it's limited. And for all the programs that are contending for space, if you're going to take information from your CPU and store it someplace temporarily, you're going to have to put it someplace where it'll fit, right? Because on any given moment, you probably have a few dozen programs running on your system, right? Whether you know it or not, right? In order to draw the desktop that you have, there's a program running to do that. In order to listen to all of your mouse clicks for all these icons on your desktop, there's a program running to do that. To draw the menus and draw them when you click on them, there's a program to do that. So you have dozens and dozens of programs that are running on your system. So one of the places that it puts the so-called execution context, EC, in EC or execution context is a copy of all this information, register file, ALU, FPU, dcache, the PC, the stack pointer, the memory register pointer, into a piece of memory called a data structure called execution context, and this is put in a special region of your disk called the backing store. Backing store. So this execution context is stored away, bless you, in this place called the backing store. So then, when the processor is done temporarily executing some program, some other program, the information from this backing store is loaded and put back onto the CPU, right? That's called context switching, switching between the execution context of one program versus the other. So the execution context is filled. It's squirreled away on the backing store or stored in the backing store. And then the CPU takes Microsoft Word, a piece of it, loads it across into the instruction cache. So that piece of Word is in the instruction cache. I'll call that W. And now it starts to read out instructions from that piece of Microsoft Word that's in the instruction cache. If data is created, some of that data, like let's say you're loading the dictionary for doing spell check or grammar check, that's loaded in the data cache so that you can do that quite rapidly on the CPU. So then when you switch from Microsoft Word to something else, of course, that execution context for whatever parts of Word happen to be executing on the CPU are stored off in the backing store. Have you ever run a lot of programs and you see after a certain point your system slows down to be doggedly slow? And if you look at your hard drive is going like working like crazy. And the reason for that is that you try to load so many programs into memory and there's so much switching happening that the CPU is pushing execution context constantly onto the backing store and reading other ECs off of the backing store. Now, of course, disk is slower than memory and slower than the CPU. So what ends up happening is your disk is working constantly, right? And because your disk is slower, it then becomes a bottleneck to the so-called context switching, and you see that slowdown on your system. Now, is some of this stuff kept in RAM? Absolutely. But I wanted to talk about this idea of what a process is and the information that you need in order to switch a process, right? So don't be afraid to put yourself out there and get it wrong. That's what learning is all about, okay? So thank you for the two of you who answered. Okay, any questions about this? Okay, so a process is nothing more than a program in execution. And in order to switch between processes, you need to save the context, i.e., all that information for the process that happens to be on the CPU when it's running. Okay, so let's talk a little bit more about process management. There are two major units of use of a process on a CPU. One is called, of course, a process. Okay, that's pretty easy. And the other is called a thread. And we'll take a little bit of a look at a difference between what those two are at a high level. And then once we get to the module corresponding to the chapter on process management, we'll talk more about the algorithms involved and the data structures involved. So going back to the previous diagram, you might ask, well, how does the operating system know when to do this switching, right? That's where the traps are concerned. So the operating system says, okay, Microsoft Word, you're going to get a standard unit of a time, delta t, could be 1 millisecond, could be 2 milliseconds, and you're, during that time, going to have full use of the CPU. All right, wonderful. But I don't trust you. And because I don't trust you, I think you're going to try to make exclusive use hogging the processor, and that would deprive all other programs from being able to run, right? Wouldn't that be horrible if you ran Microsoft Word and all of a sudden nothing else would run on your system, right? No email, no drawing of the screen, no updating the icons, none of that, right? So the operating system sets a timer and says, okay, Microsoft Word, you're going to get 2 milliseconds, and how I enforce that is I set a timer that's going to cause a trap to occur, a software interrupt, when the time expires. And only the operating system can do that because that's a privileged operation. So once that timer expires, that software interrupt or trap is generated, and then the operating system gets back control. When it gets back control, it says, okay, this particular program, Microsoft Word, has been running. The trap expired for the timer expired. Now I'm going to select a different process, a different program to run. Okay? Make sense? Okay. So we have this so-called single-threaded process. That is one sequence of instructions that can run, and you can think of a thread as being associated with the program counter. The program counter holds the address or the identifier for memory location. They're all numbered. It holds the address of the next executable instruction. So if you have a program, let's say that's Microsoft Word, and for the sake of example, the first instruction is at memory location 1 in memory, and then memory location 2 is the next instruction, memory location 3 is the next instruction. When instruction 1 is executing, the program counter will have the value 2 in this example on the CPU. Because once that instruction is done executing, whether it's an arithmetic operation, floating point operation, or what have you, it needs to know where it should fetch the next instruction from, right? Now, I'm drawing this as being in RAM, but really it comes from the instruction cache. And there are lots of primitives beyond the scope of this class for how you might fetch from instruction cache, okay? All right, so we have a single-threaded process, and a thread is associated with one sequence of instructions. And the program counter is incremented every time you load an instruction from that location. And the process keeps doing this until one of two things happen. Either the program exits, there's an exit instruction, or the unit of time expires, called a quantum, right? So that timer fires, the trap is generated, and the operating system says, okay, time to switch. I'm going to save away your execution context, and I'm going to switch to some other program, okay? A multi-threaded process has more than one program counter associated with it. Again, a thread corresponds to a sequence of instructions that you execute. So there are some kind of programs, and typically high-performance servers use threading all over the place. Many of your applications use threading all over the place. So-called multi-threaded processes have more than one program counter. There's one program counter for every single thread, right? So you can have multiple functions, if you will, or multiple streams of instructions executing seemingly at the same time. If you have more than one core on your processor, they will physically, literally execute at the same time. If you only have one core on your processor, then what will happen is that the operating system will switch from one thread to another, right, called thread scheduling, and that happens within the same delta t, 2 milliseconds or so, for which that process has use of the processor. So let me ask you, why would a program even have threads? Why have threads? What do you think? What's your intuition? Why would you use threads? So let me pose it a different way. Is your program always running? Does it ever have to pause? What can it pause for? Input. It can pause for input, for I/O. So let's say, it's trying to get the next command from the user, right? It pauses for I/O. Let's say you're writing something to the network. You have to pause for the network card to be done, implementing that write for I/O. For the disk, right? If you're going to read something from disk, you have to wait for the disk to spin up, for the read-write head to go to the right track and sector and platter. You have to wait for the read to happen, and then you have to wait ultimately for that information from disk to go from the buffer of the disk controller somewhere into memory, right? That takes time. So if there are multiple opportunities or multiple ways and times when your program is going to pause, if you had to pause, say, for keyboard input, right, then your program would sit there doing nothing on the processor for the entire 2 milliseconds, and that's a waste of your CPU. So the reason why people implement threading in their software is so that if there are parts and functions in your program where it'll pause, that other things will still happen, right? It's why your email can still check to see if there's new incoming messages while you're reading an email and scrolling. It's because of threading. Now, of course, this is wonderful, right? But as you'll see in operating systems and many other disciplines, computer networking and so forth going forward in your curriculum, every benefit has a consequence. It has a cost, if you will. And the cost of this threading is that you have to synchronize, right? Because you can have two threads trying to access the same resource. And we'll talk about that in detail when we get to the module on locking and semaphores, okay? All right. So multi-threaded processes have more than one program counter. And typically, when you run a system, it has many processes because you have many programs in execution. But each process can have multiple threads. Now, you can get concurrency by having your processes or your programs in execution execute on different CPUs if you have a multi-processor system. You can also get this concurrency, meaning physically more than one thing happening at the same time if you have multiple threads and you have a multi-core machine. Okay? All right. Any questions? Make sense? Yeah. All right. So let's take a look at the difference between a process and a thread. And typically it's the case when you see a thread, you can see a squiggly line that's vertical, right? So we have this thing called a process. You have your instructions or your code. You have your data, right? So you always have code and data. The code is, of course, the program itself, and the data is all of that information that it generates stored in RAM as you run, like you're typing a document. All of the stuff that you type, that's new data. It has to be stored somewhere. Okay. You also have your program counter, and your program counter associated with your process identifies the next executable instruction. And so this idea of your program counter is needed in order to execute code. You also have a stack, right? And your stack is used physically by the compiler in the implementation of function calls. So you're calling functions, you're executing statements, you're generating data, and you're doing that as directed by the instructions collectively that comprise your code. So typically a process has one so-called stream of execution. It's the stack and the program counter that define that stream of execution. Now it's drawn as a squiggly vertical line because if you imagine your code here, your code has instructions. First you execute instruction 1, execute instruction 2, execute instruction 3, and so forth, right? So they often draw that or connote that with a squiggly line. So that's what a process is. So let's take a look at a multi-threaded threaded process. So again, you have your code and you have your data, and then you have a stack and you have a program counter. That's one instance of your ability to execute code. You have another stack and another program counter. And then you have maybe another stack and another program counter. In this case, we have three sets of stack and program counter, and therefore we're able to execute three streams of instructions, right? Three different functions from within the same code. So in that case, you draw three of those vertical squiggly line to connote the fact that you have three threads in this multi-threaded process. Okay? Any questions about this? All right. And so similarly to a process, within a process, you have this thing called a thread context, right? And a thread context exists as one of the pieces of information for a thread. Now, if you Google searched something called a process control block, and we can actually bring this up. So let me do this. And let me bring up my browser temporarily. Oops. Linux process control block. The process control block is the name for the data structure that stores the execution context. So let me see if I can find a code listing. Uh, let's see. There we go. Let's see if this has it. Nope, that's a slide. It came up in my lab earlier when I was preparing for today. Let's see. Let me do this code. Let me see if this is it. Nope. Non-static. It's not coming up. I'm getting different search results. But anyways, you can actually look at the data structure in C that defines the process control block for Linux. It's no secret. It's open source, so you can actually look that up. Okay. Any questions about this? Make sense? Okay. So this threading allows you to pretend you have multiple execution streams within the same process or program in execution. And how you implement that in most language bindings or APIs is by specifying multiple functions that will appear to you to execute concurrently. Depending on your processor, if it's multi-core, it'll physically execute concurrently. If it's not multi-core, this process will take its unit of time on the processor and share it among these threads. And it's used in particular if you have a lot of I/O operations in your program so that you can continue to make full utilization or use of the CPU during that period of time in which your process has use of the CPU. Okay? All right. So let's take a look at some of the activities associated with process management. Um, it's responsible for creating and deleting user and system processes, right? So there are processes in the system, things like the printer spooler, which is listening for jobs that are sent to the printer. Things like your user programs, they have to be created and deleted. So that creation is the loading of it into memory, the association of it with an execution context, and the swapping in and swapping off of the EC on the CPU back and forth to the backing store. You can suspend and resume processes, so some processes can pause, right? Mechanisms for so-called synchronization, that's the orderly lining up of processes and threads to access data structures, and you can use certain constructs called semaphores and mutexes to do that, and we'll talk about that. Um, Ways for processes to communicate, so-called inter-process communication, or IPC. There are different ways of doing it, whether you're doing it across CPUs or doing it across machines, right? There's a whole course in networking where you spend a whole semester talking about IPC between different machines, and we won't talk about that too much here because there's a whole semester in the spring on that. Also, mechanisms for so-called deadlock handling. Whenever two processes or threads try to initiate conflicting operations, there's a way to resolve that, and there are primitives and operating systems to do that as well. But we won't be focusing so much on the deadlock arbitration mechanisms. Okay, so let's take a look at memory management. Now, I said to a little bit earlier that all of your program code cannot fit in memory. And the only way around this is to take parts of your program code and usher them into RAM and then execute those, right? Load pieces of them into the instruction cache. And so when we have our memory management, we have our programs on disk, and I'm just going to draw them side by side without the system bus. And we have our memory, our main memory, our RAM. Now you can just assume that when I draw an edge between these that it's going over the bus, but I'm not going to do that here for the sake of having space. So now let's say you have Microsoft Word on disk, and Word is pretty big, right? Word itself is a few gig, and if you only have a gig of RAM, what are you going to do? You can't just load Word and nothing else, right? Because you have many different things your system needs to do. So every program is logically chopped up into standard pieces, and we'll talk about another time this semester what those are called, but it's a standard size. And every program has a starting location. So then the first thing that happens is it says, okay, this program's first run. I'm going to go to the starting location, that block, and I'm just going to kind of darken that block in a little bit. I'm going to load that starting location into memory, right? So now what's going to happen, your program counter, when it's time for that process to execute Microsoft Word, it sets the program counter ultimately to point to that particular starting location from that block for Word that was loaded into memory. So then it executes. You execute the first line, the second line, third line, fourth line, and so forth, and eventually you run off the edge. When you run off the edge, it says, I'm running off the edge. Where's the second block of Microsoft Word? I'm going to now load the second block of Microsoft Word. Now you notice here, I took the second block of Microsoft Word and I virtually, through the diagram, pull it into memory. Now you notice here it's in a different location in memory from the first part of Microsoft Word. Now, it could be the case that if you don't have any memory left, it's going to load this in the same location as the other one, overwriting it, just clearing that out. Other times, the decision is, I'm going to load it in a different location. It all depends on what other things are in memory and how packed together your memory is with pieces of different programs. So that's Microsoft Word. You might have Internet Explorer, which is pretty big, and it's on disk. And it, too, is chopped up into standard size block units, and its pieces are also, this is IE, this is Word, this is Word. Its pieces are also loaded into memory, right? And again, when execution switches to Internet Explorer, it's going to execute the first line, second line, third line, and so forth. It runs off the edge, and that causes the next piece to load. And then eventually, memory gets filled up with all of these pieces of programs, and now you have to make a decision. Do you overwrite? Do you pull something out? What do you do, right? So that's what memory management is. It's the management, and that's one of the functions of the operating system, of the ushering onto memory of blocks, standard size units of code for all of your programs. Okay? Any questions about this? Yes. Ah, so when I say running off the edge, thank you for Coleman, right? Okay. So Coleman asks, Comlin. Okay, my mistake. I'm sorry. I'm going to butcher everyone's name, I promise. So Comlin. Comlin asks, um, what do I mean by running off the edge? So let me draw one program. So this is your program. Let's call that program P1, right? So let's say your program counter points to this location, and it's currently executing the location before, right? So now it loads the next instruction pointed to by the program counter, and then the program counter now changes to be that next instruction, right? So now, let's say it's done executing this instruction, and it loads this instruction that's in that last location pointed to by the program counter. So the next thing that happens is the program counter increments, and it's now pointing to a location that does not belong to process one. It has not been allocated. That causes a software interrupt, a trap. And that's what triggers, and I didn't talk about it on purpose, but that's the mechanism that triggers the operating system into identifying the next block it's going to load. So when I say running off the edge, I mean literally that the program counter has now gone to the last instruction, and now the next executable instruction is a location of memory that does not belong to that program. Okay? All right. Any other questions? Does that make sense? Thank you for your question. All right. So this memory management is the accounting, if you will, of who owns what piece of memory, right? What is the next block, where you put them on disk, and how you iterate through them in order to get programs to execute. And the whole purpose for memory management is to try to allow multiple programs that can't physically fit in RAM to allow multiple programs to make use of system memory. Okay. Ooh, time is ticking. All right, we're here till what, 10:15? So we have 1 minute left. Let's stop there, and we'll pick back up next time, uh, and hopefully finish the module. No, we're 10:50. 10 when? 10:45. Okay. Well, I'm sorry, I'm not used to teaching 9:30, so I almost got it, huh? All right, thank you. Can always count on the students I've had in other classes. So awesome. All right. So, so So memory management determines what should be in memory and when. It keeps tracks of the parts of the program that are loaded in memory and also who owns those parts. And it also decides which parts are going to be shuffled or ushered into and out of RAM. Okay? All right. So let's take a look now at storage management. That's another feature that's implemented or another responsibility of the operating system. And so the operating system provides a logical view of data that is ultimately stored on disk. Now, we say logical view because you don't have in your programs, unless you really want to, you don't have direct access to the individual platters and sectors and tracks on a disk. Now, absolutely, you could use an API that exposes that level of detail, but it's an absolute mess interacting directly with the disk. And so for the operating system, all you do is you specify a string of text, right? File.txt or homework1.doc or .pptx for the slides or what have you. Well, that's kind of nice, right? That's part of storage management. Now, the reason for this is that it's easy for us human beings to deal with text because we name things, right? Doesn't matter how funky that name is, but it's a lot easier to remember the name, homework one, than it is to remember uh, track 0, platter 5, sector 7 through 12, right? It's a lot harder to do that. And moreover, in presenting this logical depiction of data on a disk, it can now spread this file information out over the disk so it doesn't have to be sequential. So you can kind of pack things in more tightly based on where they fit best, not necessarily based on sequential ordering. So each medium, each physical storage device is controlled by a device controller, and it's hanging off of the I/O controller. And each one has various properties, like whether or not you can access them randomly, random access. Well, random access means that every location can be accessed, and you don't have to go sequentially in a particular order to do so. That can give you two things. It can allow you to pack information in more tightly. It can also speed up your reads and writes. And so if you know that you're going to be accessing information frequently, when you store it, it's kind of nice to store it someplace near where the read write head currently is located, right? Okay, so let's take a look a little bit at storage management. Now, for you, when you say, here's my file, you say file.txt. And let's say file.txt, it contains some text, blah, 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 right? To you, it just looks like one contiguous or sequential piece of information. Now, it could be actual data, like maybe it's banking information. It could be an image, right? The data from a for a picture. It doesn't matter what it is, but to you, it looks like it's continuous. Now, in reality, when you store this file, you really have pieces of a file and it's implemented as a type of linked list. So maybe blah, the first blah is stored here, and then you logically have a pointer to the next piece, blah, and then you logically have a pointer to the next piece, blah, and then you have a null for the last one. Okay? Now, it's a lot easier, certainly, to deal with a continuous tape, and that's what it looks like when you make a system call to write or to read, right? When you read something, you don't have to specify the sector, the track, and all that stuff. You just specify the name, right? And a directory is nothing more than a specialized type of name. Now, data structure-wise, it's stored as a list of pieces of a file, but then when you actually get to a disk, let's say you have 4 platters, and let's call that platter 1, platter 2, platter 3, and platter 4. And let's say you have track 1, track 2, track 1, track 2, track 1, track 2, track 1, and track 2. So each of these 4 platters has 2 tracks. The inner track we're calling track 1, and the outer track for this example we're calling track 2. Okay. So now you can take these pieces and you can say, okay, well, I'm going to put the first piece here. It's going to be on track 1, whatever sector this might be. Maybe the second piece is going to be here on track 2 on the third platter, and maybe that last piece is going to be here on track 1 on the third platter, right? So now, when you read the file, I've just drawn these pointers here as just pointers because it's easy to do. But if you were to kind of blow these things up, you'd have the data blah, and then you'd say platter P1, track 2, and say sector, let's say that was sector 5, for example, right? And at that location, you would find, here's a block, it's called block 1, you'd find block 1, right? So what we're writing here is pointers, physically, is a specification for the platter, the track, and the sector where the next piece is found. Now, of course, if you were to manage this yourself for all 3 of these blocks, it would be an absolute mess to do it, right? Whereas all you get in the APIs for the system call is just a file read, and then you just specify the name in quotes for whatever that file name is. So all of this feature about management of the track, the sector, the platter, the location physically on the disk geometry of where you put these file pieces, that's all part of your storage management. Okay. Any questions about this? Make sense? All right. So what is file system or storage management? Files are usually organized in a logical way, not only just as streams of information, but also as directories. And of course, a directory, it's a piece of text, right? And associated with that text is some location. And at that location, you find lists of names, right? And those names just happen to be files. So a directory is just a logical construct that allows you to aggregate or put together names of things, which are either files or other directories. And so using that construct, you get that usual hierarchical arrangement. So like when I log into Dropbox, I have all my DSU stuff in a directory called DSU, And underneath that, I have classes. And then under that, I'll have the semester. So fall, bless you, 2019. I have in that same directory spring 2019, and so forth. And once you open this directory, a directory is nothing more than a special file, but when you open that special file, it contains a list of names, right? And that's all a directory is physically. But from a logical standpoint, you see it as this hierarchical arrangement of things. And that's just really for our benefit, because if you had all your files for everything in a single directory, that would be unmanageable, right? It's good to be able to aggregate things hierarchically. All right. So, what do the operating system activities related to storage management deal with? Things like creating, deleting, and deleting files and directories, um, primitives or functions or API calls to allow you to manipulate these files and directories. So you can set the name, you can add things, you can change things, you can delete things. The ability to map files onto secondary storage. The mapping is exactly this layout that I described. So the operating system decides where, which platters, sectors, and tracks, these pieces of the file, where they'll go. It manages all of that and fills in this detailed information for the pointers, and you don't have to care about that or deal with that. Also, backing up files onto stable storage, right? That's typically done with an I/O controller, and you have a scheduler, and it wakes up every night or what have you, and stores it onto some type of tertiary storage, which is generally slower, but much, much bigger. Things like a tape, or if you're going to burn a DVD or what have you. Okay. Any questions about this? No? All right. So usually, if you're going to store something on disk, its whole purpose is to store things that you want to keep around for a long time, or that won't physically fit in main memory. There are other types of storage, so-called tertiary storage, which is even more long-term when you want to make archives of things. And while it's certainly relatively slower to store things to tape and to DVD, you usually do that if you want to make a backup that you're going to sit in a vault somewhere. So let's say you're a bank and you have some records, right? There's also federal law involved about how you maintain records and things like that for financial transactions. And so somewhere they will put this stuff in a separate location off-site in a secure storage that's climate controlled so they could recall it should they need to if they're ever subjected to any kind of scrutiny. And so everything on your computer in terms of the speed is hinges on the disk performance, and not only just the physical disk performance, how fast your access is for your reads and writes, but also the algorithms you use for scheduling, right? So if you have a really bad scheduling algorithm or algorithm that's responsible for deciding how things are laid out on the platters, the tracks, and the sectors, you're going to have a slowdown. And the reason for that slowdown ultimately has to deal with a bunch of things. For one, is that if your bus is slow or your disk is slow, it's going to affect the speed of the rest of your software. For one, your loads, when you load your programs, because those programs are run or loaded off a disk, if you have a slow disk, you can have slow program load. Moreover, because of the scheduling of processes, if these execution contexts are pushed onto the backing store, which is on disk, and read off of the backing store, when you're switching from one process to another, well, if the disk is very slow, then that access to and from the backing store is also going to be slow. And so, a lot of people neglect the disk performance, but it's really important to pay attention to that. Now, of course, that is not a hard and fast rule if you want a so-called low power machine. So in mobile devices in particular, it's really important to try to preserve battery life. And so one of the trade-offs you'll find in a lot of these ultra portable mobile systems is you'll find if they have a mechanical disk, that disk will generally be 5,400 RPM and not the 7,200 RPM. If you look at high-end server systems, you'll see 10,000 RPM disks on those. So they spin faster, and therefore you can get access to information on disk much faster, right? But you pay for that performance in the additional power consumption. So you will almost never see a 10,000 RPM drive on a laptop. Is it possible? Yes, it is theoretically, but almost never you see that. Okay? All right. Any questions about this? Make sense? Okay, so this is storage management. And of course, the operating system, as I alluded to with that figure about the layout of blocks of files across the platters, tracks, and sectors of a disk, the operating system is responsible for so-called free space management. Now, similarly to RAM, for disk, you're also looking at which regions of disk are currently occupied, right? And so it maintains something called a directory, right? You could call them almost like a table of contents for a book, right? Or an index in a book. And so a disk has something that looks like your index or table of contents, and what it does, it marks off the different parts of the disk as being occupied. And so the operating system also manages free disk space. And sometimes, your disk, after you're using it for a while, you have a lot of these used blocks scattered around, and you have to do so-called compaction, right? And it'll take like maybe a minute or 2 or 5 minutes to run. And what it's literally doing is taking all these blocks and moving them uh, closer to one another in order to free up space, right? So if you're using your system and you find it's getting kind of sluggish, you might want to run disk compaction, and that'll speed it up a little bit. Because as you have more and more blocks scattered around, it gets harder and harder to find free space, and it's a lot easier to kind of push them all together to free up space instead of having all of these little onesie twosie bits of space, free block available on disk. Okay. Oops. Why did I do that? Okay. So, any questions about that? All right. So I'm going to skip this slide. It talks about the relative performance of different types of storage in your storage hierarchy. On one extreme, it talks about the registers. That's the fastest storage. It's on the CPU. And on the other extreme, it's a magnetic disk, right? That's the one with the platters, the sectors, and stuff like that. That's the slowest. And it talks about the amount of storage, talks about the access time, and things like that. So I'll leave that to you to look at. It's in the book. All right. And so lastly, and I'll end with, I think I'll end with this. Let's see what time. All right, we have about 15 minutes. Okay, I'll keep going. When you have multitasking environments, you have a bunch of different programs running. And when you have multi-processor environments, you have more than one CPU running, whether it's on the same die, the same chip, multi-core, or if it's on different processors attached together or communicating with one another on a bus. You have data migrating from one storage mechanism to another up the hierarchy. So for a single processor system, you have your hard disk, and that data is loaded from your disk into RAM, right? And then it's loaded from RAM into your cache. That would be your data cache on your CPU, your L1 or L2 cache if you read a chip spec. And then from your cache, you have your hardware registers. That's your register file that we alluded to earlier as part of your CPU. And so certainly data can be read, right? But data can also be written. When you write data, of course, this data flow goes in the opposite direction, right? Down the hierarchy, and ultimately it should make its way to the hard drive because at some point you have to save this data. Now, in a multiprocessor environment, you have an additional problem. Well, you have more than one CPU. So once you get to this part of your hierarchy, you have multiple copies of CPU, right? And so one of the main issues in multiprocessor environments, one of the costs of this so-called concurrency, is that you have to make sure that if you have a value that you're working on, that it stays consistent across each one of those processors. This is called cache consistency. It's a really big deal, a really important problem when you're dealing with multiprocessor systems. So let's say you have a banking application, right? And you have a multiprocessor system, and you're engaging in a transaction to say deposit some funds. You deposited, $100. So of course, your account information, right, this A, if you will have whatever the balance was plus 100. So let's say you had $1,000, it's now 1,100. Now, of course, CPU number one knows that this value is now 1,100, but you have to make sure that CPU number two and CPU number three also get that update. So how does that happen? Well, each CPU, whichever CPU has the newest version, updated version, it triggers a send to the other CPU copies cache to update that value. Another way of doing that is that it sends a signal to say, I have an update. So when CPU 2 and 3 try to read that value, instead of reading it from their cache, they get a copy from the cache of CPU number 1, right? And so this idea of synchronizing the data among caches is called cache coherency. And there are lots of algorithms. You can actually spend a whole career doing cache consistency and cache coherency algorithms. Okay, the same thing happens in distributed systems. This cache coherency is very, very important. So let's take a look at this from a single von Neumann architecture standpoint. So we have a bus, and we have CPU1, and we have CPU2, right? And I'm only going to draw the data cache, D cache, only going to identify that. And here's the D cache in CPU2. So now, also connected to the bus, oops, we have our I/O controller, and we also have our disk, hard disk, hanging off of that I/O controller. So the first thing that happens, let's say you're doing that banking transaction, and here's your account, and you have a certain balance. Let's say it's $1,000. So CPU2 draws that into memory, and it knows that your balance is $1,000. It's now interacting through the network with you on your browser, right? So there you are. And you decide you're going to do a deposit or transfer or what have you. So that balance is now 1,100, and it's in your data cache. And of course, let's say CPU 1, let's say the bank is now trying to compound interest, it's trying to pay you, another dollar or something based on the balance that you have. So CPU 1 now needs to read that value, right? If it reads $1,000 and gives you that percentage for interest, it's going to get it wrong, because if you're getting, say, 5% on 1,000, that's well, you don't get 5% anymore, but humor me, it's $50, right? So if you think that the balance is $1,000, it's going to shortchange you, because now that your balance is 1,100, that 5% interest should be $55, right? So it's really important, if CPU1 decides it wants to look up your account balance and compound interest at a rate of 5%, it has to make sure to get the most current value, which is now 1,100, that copy that CPU2 has. So there's a system in place where CPU1 says, oh, I want to access this value. And it's told the value that you have is stale, right? So let's say CPU1 had pulled in this $1,000 account balance, right? And now it's getting ready to compound the interest. When it tries to read that value, it's going to be told, this is stale, it's no longer fresh, it's no longer good. And it's going to cause it to now pull in a value informed by this 1,100, right? Now, I'm drawing at a high level to let you know that this capability is there, and we will also talk about in detailed mechanisms of cache management and cache coherency as we deal with the further chapters in the book. Okay? All right. So that's one form of cache consistency. Let's take a look at another form, and we'll deal with this as it pertains to a distributed system. So let's say it's the same person, right? Doing a lot of stuff, you're banking online, and let's say you film a video and you want to upload this video to YouTube, right? Okay. So here you are, you're at DSU, and you're connected to the network when it works, right? Is DSU. And now DSU has a gateway router and is connected off to the internet. Now, let's say, here's the internet. Somewhere in Los Gatos, California, I can't remember where YouTube headquarters is, there's a data center, and hanging off this data center is the YouTube server, right? So you decide you're going to upload your video. Now, of course, you upload your video, and that video makes its way across the network and to YouTube's server. And if you've taken computer networking, this is very mundane for you. You upload it to YouTube server. Now, YouTube, they don't just have one server, right? They have a bunch of different servers around the country and many around the world in various data centers. So let's say you have your friend who is on the exchange program in China, right? And this is the internet. And let's say internet has connections to other networks. And this is that trunk that goes to China, right? And your friend is there's a YouTube server here, YouTube server, and that server is responsible for some region of China, right? Because you'd never load it all the way from Silicon Valley to watch video in China. So let's say your friend is on exchange here, right, with one of the partner universities, and you call her and say, hey, I have a new thing posted to my YouTube channel. So you post it locally here in the United States, and your video, let's call it vid, is here on the server at YouTube in Silicon Valley. Now, of course, this person can try to access it, but this video does not exist locally on the server here, serving a region of China. So, of course, among all the YouTube servers, they're going to maintain connections with one another and says, oh, well, this video doesn't exist here in the cache, so to speak, among the directory of videos for the China region. So I'm going to synchronize or make sure that whatever I have locally is eventually propagated or pushed to all the other server instances around the world. So the video is pushed here, and now your friend can see that video. If you updated the video, so let's say you deleted it and you changed it because you wanted to put your copyright on it or something like that, similar thing would happen. The new version, let's call it video 2, second version, gets pushed here locally, and now when your friend tries to access it, it says, hey, this is stale, and it loads a new copy with those updates. So you can have cache coherency and synchronization between caches at the individual computer level among the data caches on a multiprocessor system on all the different CPUs, but you can also have those algorithms that are synchronizing pieces of information between server instances across a wide area. Okay? All right. Any questions about this? Does that make sense? Okay. So it's 10:39. So let me end here with the IO subsystem, and then we'll pick back up and hopefully finally get through the last of the material for the intro for chapter 1, and then move on trying to squeeze in C programming, because I'd really like you to get some experience with tinkering with parts of an actual operating system. And so the IO subsystem, as we talked about, is used particularly to get information onto devices or off of devices. Interfacing with the I/O system is a so-called I/O controller, and that I/O controller manages buffers, and those buffers interact directly with the device. So let's say you're dealing with a printer. There's a buffer, and when you put information into that print buffer, it then fires up the printer, knows how to control the printer to take that data and render it as what you see as a printed page. So the I/O system, subsystem, is responsible for a bunch of things: memory management. That includes the management of these buffers associated with the I/O controller. So it stores this data temporarily. Whether that data is going outbound for something like a printer, or let's say it's a network, right? Data comes in, it's put into the I/O buffer. The I/O controller does that, and that's the incoming data from your network. And then ultimately, that data is scraped from the buffer and put into main memory, right? So you need to have some buffer management between the I/O controller and main memory. It's the transferring of data to and from the buffer associated with the controller for the I/O device. It also does some caching, right? So caching is in play. Hard disk drives use caching all the time. You have some fast memory in which you store parts of files that are on that disk, because it might be faster to load it from that bit of memory rather than spinning up the platters and using the read-write head. Now, when you look at a disk and go on Amazon or Best Buy or wherever you might want to go to look at disk specifications, don't just look at the disk speed, the RPMs. Also look at the cache size, right? Because you're going to pay more for a disk. You might wonder, gosh, well, why is this terabyte disk more expensive than the other one? Well, there are two reasons. One of them is the warranty, right? Um, it's uh, its mean time to failure. You can use it more before it starts to fail. And the other is the cache size. Look at the cache size, because that is going to impact your reads and writes, especially if you do something that's very heavy on I/O, like video editing. You want to make sure you have a generous cache. Okay. Or gaming. Some people, gaming, it matters. You also have a general so-called device driver interface. Now, the details of the device managed by the I/O controller are hidden from the user and hidden from the operating system, because you don't want to have to, you know, tinker with individual control lines for a printer. You don't want to say advance the page, select color blue 35, now spit out a pixel, right? You don't want to have to deal with things at that level. You could absolutely, but you'd never get any other effective work done. And the device driver abstracts all of that. So all you have to say, at least in PostScript, is draw a box in this location, and it knows what to do with all of the individual stepper motors inside of the printer. So it offers general device driver interface as well as for specific hardware like network cards and all sorts of other specialized devices that you could imagine. Okay, so any questions about this? No? All right, it's 10:43, 2 more minutes, let me end there, and I will see you all on Thursday.